Okay. Now, when it happens that the second medium is a transparent medium, when the second medium is a transparent medium, such as light moving from air to glass. Medium one is air, and medium two is glass. Then, when the light hits at the boundary, and this is the boundary between medium one and medium two, 1 and 2. Part of the incident light is reflected. So part of it is reflected. And a greater part of it is refracted. A greater part or chunk of the incident light is refracted. When the part of the light is moving from a less dense medium, air, to a more dense medium, glass or water. Okay, so this will only happen when we have two different media of different densities. So we define refraction as the bending of light as it moves from one medium to another medium of different density. Sometimes we add optical density because we expect the light hitting the boundary to be seen by an observer to appreciate that, yes, truly the path is bent. Okay, because if the second medium is a denser material, example, wood or block, because wood or block is an opaque material, you cannot perceive the light at the other side. So the denser material must be such that it allows light to pass through them. The reason for which sometimes we add optically denser material. Class, are we okay?
Yes.
Studio.
Hello.
So when it moves through maybe of the same densities, do we
Yeah.
consider that as a fraction of light?
No, it won't bend. There wouldn't be any bending. The light will just pass through it.
So it's
Okay.
it's not a fraction of light.
Oh, but what is refraction? Refraction is the bending of light, or when the speed of the light changes from one medium to another. But what I'm saying is that if we have the two materials having the same density, there wouldn't be bending at all. Are you okay? Okay, are you okay? There wouldn't be bending for you to call us either reflection or refraction. All right. So that's it with refraction of light. All right. Now, when the light passes through the media, the two different media, let's see, please let me take a shot of attendance and then drop it in a group. Attendance today isn't encouraging, and it's another medium of different optical densities. So when the light moves from one medium to another, its direction can change, its velocity can change, and its wavelength can change. But before this must happen, then the two media involved must have different densities. How are you okay?
Yes, please.
Must have different densities for this to happen. All right.
Mr. Dear.
Hello.
Please, you said the latter part, medium of different. I didn't get the latter part of the
Different
for the refraction.
different optical densities.
Thank you
Optical
very much.
densities. All right. Now in experiment and then in theory. Experiment and then in theory. Whenever light passes from one medium to another, this is a normal. You know, whenever you want to draw a ray, because you talk about incident angle of incidence and angle of refraction, there is a need for the normal. This is a boundary or the interface between the two media. When the light is propagated from a less dense, a denser or a rare medium, let me use less dense medium to a dense medium. So when the light is moving from, this is the incident ray. So the light is moving from, example, less dense medium, let's take something like air, and then dense medium, glass. The change is such that the change in direction or the speed is such that it is bent, the refracted ray is bent towards the normal. So when light ray travels from a less dense medium, a less dense medium to a dense medium. The refracted ray bends towards the normal. So over here, this becomes the incident ray, and this is the refracted ray. This angle becomes the angle of incidence, I, and this small angle becomes the angle of refraction, small r. Please, class, are you okay? Now, I want somebody to help me brainstorm something. Why do you think when the light is moving from a less dense medium to a dense medium, the refracted ray is bent towards the normal? Why? Yes, anybody? Why is the refracted ray bent towards the normal whenever it moves from a dense medium to a less dense medium? Anybody? Chrysler. Chrysler. Lizzie. I want to pick your brain on that question. What do you think? Now, when the light is moving from a less dense medium to a dense medium, the part of the light is bent towards the normal. Why?
Savior, please. I think because it's moving into a dense medium, like its speed will be reduced. So I would have to bend towards the left.
Hey, Ursula. Yes, there are three things. Either the direction is changing, the velocity is changing, or the wavelength is changing. So you have said the same thing, but the reasons you haven't given to me. Okay, Lizzie. Lizzie, let me pick your brain on the question. Hey, Lizzie, you are here. Okay, Ajua Asante.
Savior,
Uh-huh.
I don't understand the question. Like, what are you supposed to explain?
The question is that when light is moving from a less dense medium to a dense medium, the path of the light is deviated towards the normal, right?
Yes.
Why? Why is the refracted ray bent towards the normal? So the incident ray, the refracted ray, and the normal at the point of incidence all lie in the same plane. The second law, so laws of refraction. The second law is that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant Okay, it's a constant for light moving from, or for light ray moving from one medium into another medium of different densities. The second law is what we call as Snell's law. Snell's law. This was named after a friend, a good friend, known as Willibrod Snell. So Snell's law says that whenever light moves from one medium into another medium of different optical densities, then the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. All right. Class, is that okay?
Yes, please.
Please, any question? So Snell's law in mathematical form. Snell's law in mathematical form is given as sine I on sine R, and this is equal to a constant. So the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Can I clean the board?
Yes, please.
I have to manage my board properly. Under reflection of light, we learn something about deviation, angle of deviation. So under reflection of light, Ekwe what is wrong with this girl's network? If this is a plane mirror, normal, when you incident light, I, R, but I and R are the same. So how much is it deviated when we extend this line? We realize that the angle of deviation is equal to this, which is equal to 180 minus 2i or 180 minus 2r. Under refraction, if light, this is the normal, is moving from a less dense medium so rare medium or less dense medium to a denser medium, to a dense medium, it will be deviated towards the normal. Now, if we have to extend the incident ray, Adwa Otubi, are you there?
Yes.
This is angle of incidence. This is angle of refraction. But we can argue that this angle is equal to this angle by vertically opposite angle rule. So, by vertically opposite angle rule, I must be equal to, let's assume we don't know, or let me represent this by sigma. So I is equal to R plus sigma. Let's make sigma the subject. Sigma is equal to I minus R, where sigma is the angle of deviation. So sigma here is the angle of deviation. So it means that under refraction of light, angle of deviation sigma is equal to I minus R, where I is the angle of incidence. I equals angle of incidence R is angle of refraction. And sigma equals angle of deviation. So under refraction, this is it for the extent at which light is deviated. For refraction of light, we have 180 minus 2i, or 180 minus 2r. Class, I hope you are okay here. Hello, are you okay?
Yes, dear.
Hello.
Yes.
Anakuya.
Please, can you bring the camera down to write something on it?
Are we there?
Yes, please.
So you identify how to determine deviation under mirror and deviation, or under reflection and deviation under refraction. So, Lizzie,
Yes, Mr. Dear.
state Snell's law for me.
Okay. Um, Snell's law states that when a ray of light enters a medium from another medium, the incident ray and the normal ray to the interface at the point of incidence, and the refracted ray are all in the same plane.
Lizzie, I said Snell's law. Nanopi, are you done writing?
Yes, please. Thank you.
Lizzie, I said Snell's law. Snell?
Yes, please. I said it states that when a ray of light enters a medium from another medium, the
No,
inci-
Lizzie, no. You are giving me the first law of refraction. I mean, the second law, which is Snell's law.
is
Okay.
it the
Mhm.
ratio of
Eh, eh,
sine of the
eh,
angle?
Exactly.
Oh, okay.
That is
The
Snell's law.
Oh, okay. So it states that the ratio of the sine of an angle of incidence to the sine of an angle of refraction is a constant.
But there's a condition to it. There's a condition for this to happen.
Oh,
Uh-huh,
when
uh-huh.
when a ray of light enters a medium from another medium.
Yes,
Um,
it isn't complete.
hmm.
Uh-huh. Yeah, somebody to add on. What's the condition? The two media must have different optical densities for this to hold. Okay, so for the ratio of the
Yes.
sine of the angle of incidence to the sine of the angle of refraction to work, the two media must have different optical densities or densities. Lizzie, meaning that if they don't have two different densities, it won't work. I told you the light will never bend in the first place. Class, are we okay? So
Yes, please.
the ratio of the sine of the angle of incidence to the sine of the angle of refraction must be equal to a constant. Okay, okay. And this is whenever light moves from one medium into another medium of different densities or optical densities. All right. Now, and this ratio is what we call as the refractive index. So the constant value when light travels from one medium to another, the sine of the angle of incidence, the ratio of the sine of the angle of incidence to the sine of the angle of refraction. We are saying this ratio is equal to a constant. This constant sine I on sine R. This constant N is what we call as the refractive index of the material. So the refractive index is equal to sine I on sine R. Now the question is that what is refractive index of a material? Okay, or what does it mean? What does the ratio means at all? What it means is that we define the refractive index of a material as the measure of the material's ability to deviate the path of light as compared to deviation by air. So over here, we are looking at comparing how that material can deviate light compared to how air would deviate light. So the refractive index of a material is the measure of how a material or a given material can bend can bend can bend light as compared to air. So if you take glass, for instance, we are looking at the ability of glass to bend the part of light incident in it compared to how air does it. Class, are you with me? Light ray. Please, are you with me?
Yes.
So we say that the glass has a refractive index of 1.5, absolute refractive index. The refractive index of glass, N of glass, is equal to 1.5. What it simply means is that glass can bend light 1.5 times than air. That is all. Okay, the refractive index of glass is 1.5. What it simply means is that glass can bend light 1.5 times as air. The refractive index of water, N of water, is equal to 1.33. What it simply means is that water can bend light 1.33 times as air. That's the meaning of refractive index. That's the meaning of refractive index of a material. Any question? Please, any question? All right. Then let's go into what we mean by absolute refractive index. What we mean by absolute refractive index. So Adwa Otubia. Adwa. Hello, Adwa. Adwa, the refractive index of the material is 1.7. Adwa, what does that mean? Or let me be specific. The refractive index of, okay, a given material A The refractive index of A is 1.7. Adwa, what does that statement mean? What does it mean? Tell me what's the meaning of, or is the meaning of that statement?
Means the material can bend light.
Go ahead.
Means the material can bend light 1.7
Times as air. Is that okay? So it can bend light 1.7 times as air. All right. Absolute. Amma,
So if you say, for instance, water bends light 1.33 times as air, does it mean that the water, air and the water, they are equal? Like their refractive index is equal?
they are not. The refractive index of air and vacuum is 1.001. So if you are saying the refractive index of water is 1.33, then it means that there, water can bend light 1.3 times, okay, as can be done by air. That's what it means, okay?
Okay.
Absolute refractive index. So whenever light is moving from air to glass, so we are looking at less dense medium as against dense medium. Please, when you see a less dense medium, we are also referring to rare medium. A rare medium is a less dense medium. So if the light is moving from air to glass, when the light comes into the glass, each part will be deviated, right? But how would the deviation look like? Eresi, how would the deviation look like when the light is moving from air to glass?
Sir, please, from air to glass, it will be further away from the normal.
Air to glass or Eresi?
So then it will be closer to the normal.
Where we see it.
Because I'm
It will be-
confused.
it is moving from a less dense medium to a more dense medium. So what will happen to the light going through the medium?
It will move closer to the normal.
So it will move bend towards the normal. Okay. Now, from Snell's law, if we have to find the refractive index of the material, of the dense material, the refractive index will be equal to sine I over sine R. So over here, we are expressing the material's ability to bend light with respect to the directions of the incident and then the refraction. Don't forget, I is angle of incidence. R is angle of refraction. So the I and R means direction. They are angles. Angles give a certain direction. So over here, we are expressing the refractive index in terms of direction. Now we can also express the same refractive index, this time in terms of speed. When light is moving from air to glass, the speed of light in air is greater than the speed of light in the medium. So speed of light in air over speed of light in glass. Over here, we are expressing the refractive index in terms of speed. So we say the speed of light in air is denoted as c. So under geometric optics, when you see c, we are referring to the speed of light in air. Then the speed of light in a material is indicated as v. Okay. Another way we can express refractive index is in terms of wavelength. In terms of wavelength of light. So wavelength of light in air over wavelength of light in a medium. So we have expressed refractive index in terms of three different aspects, as in direction of light in air, direction of light in a medium, speed of light in air, speed of light in a medium, wavelength of light in air, wavelength of light in a medium. So N is equal to sine I on sine R, which is also equal to C over V, speed of light in air, speed of light in a medium, which is also equal to lambda. The symbol for wavelength is lambda. The one lambda. And that's the symbol. It's a Greek word, lambda. Wavelength of light in air over wavelength of light in a medium. Okay. Now, look at one peculiar thing. Over here, what is the first medium in consideration? What is the first medium here? Class, what's the first medium? Good. Now, when you are determining the wavelength of a material, the refractive index of a material, and the first material from where light is coming from and is entering a second material. When the first material or medium is air, then we talk about absolute refractive index. So the absolute refractive index of a material is the refractive index of that material when the first medium through which light is propagated from is air. Okay, so when the first medium through which the light is being propagated from is air, then we are talking about the absolute refractive index of the material, its actual bending ability. It means that we are comparing the material's ability to deviate light to air. So when the first medium is air and the light is coming from air to glass or air to a denser material, then the fact that the first medium is air, then we are talking about the absolute refractive index of the material. Please, are we okay?
Yes, please.
Mr. Adua,
Oh, hello.
please come again.
So for absolute refractive index, light ray must be propagated from air to another material. So it must strictly be from air to another medium. And that is to talk about absolute refractive index. So if the first medium, or if the light is not coming from air to another material, class, you cannot talk about absolute refractive index. Are we okay? Anepe,
Yes,
are you
Yes,
okay?
please.
And the
Yes, please.
absolute refractive index of a material is the material's real refractive index. Its real refractive index. Its real or actual refractive index.